Um, yeah, it's about time. Started here. Yeah. Yeah, I'm gonna start. I'm waiting for a few more people, but I've got the stream going now. So kind of some announcements. I've been trying to look at scheduling stuff, make sure everybody kind of knows where we're at. So we're at the week before spring break. There is an assignment due in this week. We'll talk more about that today. I was going to continue on talking about linear regression. Actually, we're going to get into polynomial regression today. So this week, and then is talking about actually some of the stuff that will be for the next assignment after this. So because of the kind of the late starts, I'm squeezing this a little bit more than I wanted to. But so we're going to have assignment 3 due at the end of this week. I would normally give 2 full weeks, but not including off for spring break. But I am going to make the 4th assignment due at the end of the week after we get back. So technically 2 weeks, but that includes the week of spring break. So sorry about that, but yeah, I can't really make anything else work out except for do that. So there, that you should be able to see the assignment 4. I mean, I would encourage people to maybe at least maybe accept the assignment before you go on spring break. Although do take some time off. Don't take a little bit of a break on spring break. But that should be up there, and then that would be due the Friday after we get back.
And when is
I'm going to move that, so we'll do that the next week after that. So we'll have a week, the second week after spring break. We'll kind of do a review and just do the midterm tests. I don't have the dates quite right for all the stuff. I just realized that I misscheduled stuff for things here, so I need to move a few things around a bit. So, but I am planning on just assignment 3 this week. Then we'll do kind of this doing regularization and talk about polynomial regression this week, and have that assignment due when we get back. And then we'll do the midterm the week after. Anyway, so that's kind of my plan, and I'm going to have to squeeze something out here. I thought I had everything worked out, but I have to maybe remove something I was planning on doing after that. Okay, and another thing, I didn't quite get this announcement posted up here, but I'm going to try to, from this point on, kind of discuss a little bit each week about the class project. I'm going to try and maybe give some additional hints, recommendations, or even requirements about stuff to do. So for one, if you're listening to this after the fact, or let me see if anybody's joining here. But yeah, so if you're seeing this later on, so don't forget about the class projects. It's better to keep continually working on these, right? So I mean, part of the grade will be, did it look like you did 1 or 2 commits like the few days before it was actually due, or were you actually doing it incrementally? So kind of thinking about it a little bit each week from like this point on forward, right? So, I mean, I can tell that from your commit history and stuff, but usually it is a better project. People that are, spending some incremental time with it rather than trying to do it all in a couple of hours in one go, right? So keep that in mind. So, I mean, my plan, my hope is maybe I'll mention something and kind of add on to the stuff that I'm usually looking for. So, everybody should have accepted that final project, that class project. At this point, I think everybody has, if I remember right, although I maybe haven't given feedback to everybody yet on the data set that they selected. So since we're still kind of starting out on that, I would recommend that you put some thought into kind of your organization of your project. If you Google like Python data science project best practices or organization, you'll find lots of thoughts, recommendations on how to lay out your directory structure and kind of what should be in there. So I'm not asking you to do anything too complicated on these final projects So, a lot of this stuff might be a little bit overkill that you would read about here, although I would still recommend you to maybe do a little bit of these things. So, for example, you maybe don't really need to have testing, like unit tests set up in order to do data validation or stuff like that. But you might want to put in a little bit of that just to read about that and get an idea of how that works in a bigger data science project. And that kind of stuff looks good in terms of me evaluating the project that you have. But today, one thing that I often do run across is if you do use stuff other than the basic libraries that are set up for you, put some thought into making certain that you specify what the environment needs to be. Okay, so there are standard ways to set up and specify, okay, we need these libraries, these versions and things. So when you accept the assignment, the repository is created for you, there is this environment.ynlive file in there. Because for the assignments, I use the Conda package manager. So in these dev containers, this Conda package manager gets installed in there, and it can use that environment.ynlive file. So if you look in the Docker file, so if you look in this dev container Docker file, in our projects, in our assignments, and in the class repository, that's where it's actually picking that up from. So when it does a Conda environment update and you get an environment.yml file, it will look at the versions in that file. So like here's my 574, so our class repository. So basically I'm saying that when I did this stuff, I'm using this particular version of Python, and then the correct version of all these for a Python 3.12, libraries also should be installed using the Conda package manager so that we have these particular libraries set up. So, that's what this file, you can go ahead and use that, although, again, if you're using other stuff than what I gave you in the environment.ynl for the class project, make certain you're correctly maintaining this. So if you do some additional libraries, the one I gave you in the class project probably doesn't have anything in here, so maybe Python, Matplotlib, and Pandas might not have, and scikit-learn might not have much more than that. So any other stuff, you need to make certain you maintain that. So an alternative that is maybe better actually for simpler projects. So you'll also see people use requirements.txt file. So this uses more base Python. You don't have to have like Conda package manager. So you can use either or both. Although if you're using both, you have to be careful that you don't have a difference between the one and the other. But the standard way to use a requirements.txt file is using the pip, which is kind of the basic Python package manager. If you're familiar with that. So usually what people do with that is they create a Python virtual environment and then they install exactly by hand the packages and stuff they need. And then you run this command and this will figure out exactly what the library versions are and the packages are that you have installed in your virtual environment. And then when you're resetting up the project, you can do a pip install and pass in that file again. So a similar thing to what I showed for the Conda. So this will look at that file and do pip installs of the particular versions of the libraries to try and recreate the exact environment that you were using for the project, for your notebooks or Python scripts or stuff like that. So, all right, but yeah, I put some thought into that. So I'm always, because I do, when I evaluate these, I do clone the repository, but I also set them up and actually try and run your notebooks or other code and stuff that you have in there. And if I can't run them because it's not clear what packages you're using, I have to go figure it out and do pip installs by hand. I might not take the time, or I might dock some points or stuff like that. Right? So keep that up front. And I didn't complete this announcement yet, but the other thing is, Google about the basics that should be in like a project README. So you might need to redo the README that I gave you. So one of the things that usually should be at the very front top of the project README is instructions for setting up the project. So you got to put that in there and say, okay, I'm using this requirements.txt. So, after you clone, do this in order to get the environment set up, and then do this to run the scripts or whatever. Is that so? So I'll add on to that, but yeah, I would recommend maybe this week put a little bit of thought into that. Keep that in mind, but do try and make it clear and not just a description of what needs to be done, but use the mechanisms that are given, like in Python, for actually specifying the versions of the libraries and which libraries you use, and being able to recreate those. That just makes it a lot easier for other people to come in and recreate the work you've done. Makes your work more reproducible. So this is part of reproducible data science, these sorts of things. Here to talk about that kind of stuff. Okay, so yeah, so let me know if anybody had any questions about that. Like I said, my goal is I'll try and maybe post something or talk about that each week, just to kind of keep reminding people about keep your final project in mind, try and keep doing a little bit of work on it, certain things to do. So, and yeah, I might add some additional requirements, or at least recommendations of stuff to do. Okay, so let's get back to new stuff, and we can continue talking about the assignment 3, although this is going to be stuff more for assignment 4 that I'm going to jump into here. Yeah, so yeah, I don't have the assignment up, but if anybody has any questions on assignment 3, let me know. We looked at pretty good detail of that last week, of the specific functions and things. If I have some time at the end, I can maybe bring that back up and see if anybody has any questions on the assignment 3. So for the next assignment 4, it's really going to be about regularization, and we're going to be doing some nonlinear regression. So I'm going to talk about that today, and get started on that today. But yeah, all this, and including, and then the week after spring break, we'll still be talking about, we'll still be in the same chapter, although our textbook also kind of folds in logistic regression, which is really a classifier. So we'll talk about some of that stuff after spring break when we get back here. But yeah, I believe that stuff is also still in the in our same chapter here, yeah, the chapter 4 of our hands-on machine learning. Okay, let me go ahead and bring up our notebooks then. So just to review a little bit, we kind of went through the gradient descent. Like I mentioned last time, if there's maybe one thing in this class, sort of this linear regression and the basics of how gradient descent optimization works, is the one topic that I would hope everybody from a basic machine learning course kind of understands at a deeper level, for a graduate course. So, so let me know if people had any kind of remaining questions about the stuff that we talked about there. So, we'd looked at, I think we hit pretty much all this stuff. I hadn't talked about some of the, let me go through about the mini batch and some of that stuff. We hadn't exactly talked about those things, but this is a good thing to keep in mind, to be able to visualize. This is usually how I visualize these kinds of optimizations. So not all fitness functions or loss functions or cost functions are as well behaved. So the one of the reasons why the root mean squared is used is it really gives a cost function that's guaranteed to have exactly one global minimum. Right, so it looks like in 3 dimensions, or in 2 dimensions, it gives you a bowl shape. And higher dimensions, you still have one global minimum. Right? So there is actually one answer if you're using the root mean squared error for linear regression of what the set of parameters will be that will give you the absolute minimal cost that you can get. So the absolute best line in terms of the error function that we define. So when we get into more complicated things, support vector machines or other stuff, the cost functions get a little bit more, have more terms and things, and they might be messier. There might be more than one minimum, and there might be some minimum that aren't global, right? So you have more than one, and some of them are better than others, right? So then you get into having to talk about better optimization methods or methods that can find minima at different locations in the cost landscape. But yeah, this may be a little bit beyond the scope of a course like this, but it is good to understand the basic ideas of cost functions and the idea of calculating the gradient. So the derivative with respect to each of the parameters and how that's used for an optimization technique like gradient descent to follow that to a minimum. And again, if you have a function, so this is really the representation of the derivative of the root mean squared error cost function. So if you have a more complex cost function, you might be able to analytically derive get the expression for the derivative like this, but you can usually still apply optimization techniques. Just to finish this up before I go on to the next stuff for this week here. So you'll hear these terms. We won't use a lot in this class, but a pitch for also if you're interested in like deep learning, we are going to be offering deep learning this summer. Although it's a 5-week course, so it's a bit kind of quick. But we use much more in that. We get much deeper into like mini batch and stochastic gradient descent and some other stuff on that. So that's a really good kind of course to do after this one. So we end up kind of ready to talk more deeply about neural networks at the end of this course. And then we start in that course in the summer by talking, looking at neural networks and then so-called deep neural networks. So yeah, if you're looking for a course in the summer, definitely consider it. Makes good continuation of the stuff we're talking about here this spring. So in your assignment, you only had to do just a basic gradient descent. So in more complex situations, when you have large amounts of data, it might be too costly to do the calculation of the derivatives for the whole data set at one time. So the previous expression that we gave was giving the way to calculate the derivatives for all the data. So what is often done, like if I have millions or billions of data items that we're training with, is we'll do it in small batches. Okay? So that's really what stochastic gradient descent is. So the stochastic comes from, we usually select the batches at random. Right. So, like in stochastic gradient descent, if I have a data set with 1,000 samples, I might have a batch size of size 10, let's say. So we'll select 10 at random, leaving 990 Right. So the normal way that stochastic gradient descent works is an epoch will train the whole 1,000, but we'll train them in small batches, 10 at a time. So we'll select 10 at random, and then the next time we'll select another 10, but we won't reuse the 10 that we did for the first pass through for an epoch here. So here the iterations are, we're selecting these mini batches, and then once we've done that, so at this time when we select another 10, we have 980. So within the inner loop here, once we've selected all these, that's still one epoch, like you do on your assignment. And then you'll redo that again. For epoch 2, you would consider everything again and select mini batches at random. So if you look at this code, there are different ways to do it, but you can do it pretty nicely in Python. So like here, we're basically just creating an array of indexes. Yeah, look at this. So this one is maybe not quite doing the mini batch that I was talking about. This one I think is just selecting some number at random here. Oh, yeah, sorry. So the discussion, if you read in the textbook, so when you're doing this kind of mini batching, you can think of it as a range, right? So at the one extreme, you can just select one of your items at random, which is what this first version is doing here, right? So that is the stochastic. So you just select one of your items at random, perform the gradients and do an update step, and then we select another one at random. And this version here, which is I think from the textbook, is not even making certain that we don't reselect another one at random again here. So it might, within an epoch, might train multiple times on one of these and not train on some others. But then, right, so I was describing mini batch, where you do a fixed size. And the first version of gradient descent that we looked at is just doing the full batch, right? So if you don't select smaller batches, if you just do all of your training set, you're just doing a full gradient descent. So that's kind of the extreme. But yeah, this is really stochastic. If people prefer the stochastic gradient descent, probably just select only one at a time. The problem with stochastic gradient descent, I don't know if this example shows it very well, but there's a lot of noise. So the smaller the number of items that you use to calculate the gradients on and take a step, the more likely it is to be taking you in directions that aren't very good. So you'll see that the loss functions, so this is an example of a learning curve, if I haven't mentioned this before, where for each of the steps, we're calculating what the loss is at the end of the step. So when you're taking small batches or just taking one at a time, there's going to be a lot of noise. So you'll see the updates, that the cost might even increase if you're doing step one. So at the other extreme, if you're using all of your items to calculate the gradients to take a step, that will reduce the noise, but it's a lot more costly to do that. All right, so most of the time, when in real situations, when we have a large number of samples that we're going to train with, we will need to take some batch, a mini batch, but we want it to be sufficiently big enough so that we don't have too much noise in our updates, but small enough so that the calculation is reduced enough that it's reasonable to calculate the gradients and take a step here. So yeah, the mini batch is what I was just describing there. So this is taking batches of some batch size, which is a parameter here, and this hopefully is doing so this basically just shuffles the indexes. So now they're randomized, and then we take them 10 at a time. You think of this as taking the original input data, shuffling it into a random order, and then taking the first 10 random ones, the next 10, or whatever the batch size is on the inner while loop here. Okay, so, but yeah, just to summarize on it, it's good to kind of know the terminology. So we talk about gradient descent, and there's really stochastic. Gradient descent is kind of the one end where we just don't take any batches. You just update using all the data. Stochastic gradient descent is on the other end, where you just take one at random for each update step, and then mini batches is what's normally used. It's kind of a in between, is kind of a compromise. So by taking mini batches, you won't have as much noise in your updates for the costs as you're iterating over your epochs, but you will reduce the calculations overhead that you need to calculate stuff. So yeah, this one here was, we were doing the results of the mini batch. So you notice that we don't have the all the noise in there, right? So with the batch size sufficiently high enough, that's kind of what you want to see. So if your learning curves are looking like the previous one we had, this was the full batch. This was full batch descent here, I think. So yeah, if you're getting some noise in there, it can be tougher to tell whether, okay, I'm making progress, or if I got stuck in my optimization. So that kind of noise is a bad thing. All right. So let's go ahead and move on then to the new stuff. So there is some more stuff in our next one here about learning curves. Let's look at let's move on to the polynomial regression stuff here. We haven't had a chance to check if this notebook is running or not. Let me rewrite it here. It's not running. Looks like it is. Okay, so this stuff is, we're beginning to really talk about stuff for the next assignment 4. So in fact, the stuff we have to do in assignment 4 is pretty similar to the example that are given in this notebook. So first of all, a lot of students I know are surprised at this statement here. So you might have come across when doing fitting a line to a set of data, so doing a linear regression, but the same optimization, the same cost function that we looked at can actually be used to perform to fit a nonlinear model to a set of data. So this is how this works, and that's what we mean by polynomial regression. So we're actually, instead of having a linear model like we did before, we're going to fit, in this case, a quadratic. So a polynomial with a squared term, and a term to the power of 1, and a term to the power of 0. But notice x here, one thing I should point out is we're back to only having a single feature. Okay, so at the end of your assignment 3 that you're working on right now, we have our housing data where we have like the size in square feet. That's our first feature. We have like the number of bathrooms, and we have the income, the person in the house, or something like that. We have like 4 or 5 features, right? And we call this x1, x2, x3, right? So here we're back to a single feature. So this is only one feature. We can do a polynomial regression if we have multiple features, but we'll talk about that later, or maybe in the next one. So think about, we're back to kind of the case where we want to fit, in this case, instead of fitting a line, we want to fit a parabola. So we want to fit a quadratic function to a set of data. So we need terms. So you can think of these for now. We'll just call that ABC. Right? So this is our squared term. We need to figure out the best value for this first set of data, and the best value for our x to the 1 term, and the best value for our x to the 0 term. So, and this is also pretty much the same thing as we're doing in our next assignment 4. Just to illustrate this, so instead of using housing data, we're going to make up some data. So in this case, we actually know what the correct function is that was generating this data. So we have this function that's a quadratic, so it's something to the squared. So 1/2 x squared, 3/4 x plus 3 for the constant of x to the 0 term. So we know, but to that we add some noise here, right? So in a real data set, we wouldn't have points that are exactly on the nonlinear function that we're trying to fit. Right? So this is really a parabola. So if we remove the noise here, just to make sure this is clear. So up here. So this last step here, we add in a little bit of noise, which is the noise here is just a normal distribution. So it has a mean of 0, standard deviation of 1, and we scale it. So now it has a mean of 0, but a standard deviation of 0.5, right? But we could remove the noise by scaling to 0. So this really doesn't do, or I guess we could just comment that out as well to get the same effect here, not add any noise. So if you look at that, so what's really being generated here is we've got points on a parabola, a quadratic function here, and the sample points are at random on this range. So this is our x. So we just pick random points from -3 to 3 here, and plotted. But then, so to make it more realistic, or a real data set that was nonlinear that you might want to fit, there would be some noise. So either the noise from the measurement can add noise, or there can be other sources of noise in a real data set. Right? So besides the feature that you're trying to predict, there might be other features that you don't have access to or can't measure. So that's where this data set is coming from. So what we would like to do is fit a nonlinear model to this. So so the first thing for doing this kind of fitting a model to the data is you have to make a decision on the what level, for your parametric model here. Do I think it's a quadratic? Do I think it's a higher polynomial would give the best function, right? So I mean, there is a meta decision that you have to make here, right? So by looking at this, I mean, we could fit like a power 3 or power 4 polynomial if we think that this data is nonlinear. It definitely looks nonlinear, right? So people don't kind of know what I mean by that. The line is not really a good, because it goes down for a bit. It looks like it goes down for a bit of the range. It goes up for a bit here. But I mean, it could be that cubic would work here or better, depending on the data set. But that's so if we decide that we want to fit a polynomial, we can basically we have all the tools that the stuff we talked about for linear regression, we can apply the same optimization and the same cost function. So all we did here was we're making a point about, so this was actually the true function. And then after we add some noise, the points look like this, right? So the best model that we could go, in this case, for real data, you don't know the true function. There isn't really a true function that generates. We're just trying to give it the best model possible. But in this case, for illustration purposes and for our assignment 4, there really is an actual real model. So we know what the truth is behind what would be the very best model in terms of in this case, we need 3 parameters, right? So back to this, if we don't know what these are, we have to do an optimization to figure out what I call ABC parameters. But like we did for the linear regression, you can think of those 3 parameters. There's an infinite number of possible quadratics that we could define, right? But we can use the same cost function, right? So for a model and a point, we can figure out the error and calculate and use the root mean squared error. So a model that minimizes that is better than a model that has a bigger average root mean square error. So the same cost function will be used in this case. So in fact, that's really what the polyfit function is for, right? So we used that example in the previous notebook to fit a degree 1 polynomial, so to fit a line. So if I want to fit a degree 2 polynomial, using NumPy's built-in one for this, you can call polyfit. So again, I don't know exactly, it's using some optimization technique, probably similar to gradient descent, to do this fit here. So this is the data with noise. And it tells us that the ABC comes out in this order here. So you see it's pretty close. Remember, there's 1/2 and 3/4 and 3 here. So one point about this, with noise in here, you don't, this isn't surprising. You can't exactly reproduce the unknown function when you fit this. Because you don't know what function generated this, so the noise, this is the best fit for the random noise that we actually had. And it's pretty close to the true function, but it's never going to be exact. You'll never be able to exactly reproduce the true function that generated the underlying data that has noise added to it. So yeah, again, you can look at, so this was the true secret function, this was the function that the polyfit gave us here, the dashed line. Close, but not exactly right on. But also, I mean, this is using basically the same kind of optimization that we're talking about here. This is going to be the kind of the best function that we come up using a root mean squared cost function, the one that polyfit comes up with. So so yeah, it's similar. I mean, back to this, when we talked about multiple features for linear regression, we added the idea of we had multiple parameters, theta 0, theta 1, theta 2. So we do the same thing, but now we're going to be thinking of this as the x squared term. So if we have just a single feature, just down here. But yeah, like I described there, we're setting the same thing, but we're using theta 0 times x1 squared, theta 1 times x1 to the 1, theta 2 times x1 to the 0 power. So the same form, but our prediction is, we're predicting using a quadratic model to the square power here. But we want to come up with the same 3 parameters, or 3 parameters in this case, theta 0, theta 1, theta 2, which is the parameterization of our x squared, x to the 1, and x to the 0 power. And that's really what the polyfit function can number. So yeah, part of the fourth assignment. We really need to add in by hand, if we're doing this sort of polynomial fitting, we have to add in these features, right? So we only have our feature x, or I call it just x1. Right? So if we have one feature, I call it x1, right? So I think one thing you're supposed to do on the assignment 4, there is a thing called polynomial features in scikit-learn that basically does this, right? So if I have a set of features, so these are the first 5 from our random noise, right? So x was 2.3 and so on. And then, so the square of that, if I need to have my square terms for this theta 0 here, you just directly square it. I could create an array by hand, so can we do that? So here, if I needed to, I could combine those as 2 columns. So what I need is, for my original data that only had the x's, one column. So x is it's just a vector, or you can think of it as a column matrix at this point. 100 samples, each of them with a single feature, the x. So I need, in order to perform the polynomial fit for the quadratic, I'm going to actually need, I'm going to need 3 columns. I need one for the constant, the x to the 0 term. I need my original x's, but I also need these x squared. So I'll need 3 columns, 3 features for the polynomial fit. And that's what the polynomial features does. So the result of this is it's only going to have 2 columns, because we don't have to add in the dummy feature by hand. Scikit-learn does that for us. If we're doing this for stats model, we would have to also add in another column for the constant. But here, so all that's happening here is our x poly uses polynomial features. Since there's only a single feature in the original x, we end up with 2 columns. So the original data and the square of it are in, ends up being like column 0 and column 1. Also, as an aside, now that I'm looking at it, I mean, when we use scikit-learn, the order is going to be reversed like it was before. So we'll end up with the constant term as the theta 0 parameter, and then the squared term is the theta 2 parameter. But yeah, the point being that that's all just leading up to, again, it might be surprising, we can just use the linear regression, because the linear regression is just doing a fit using a mean squared error function. But it'll work fine if we pass in these features here, the squared term feature and the original feature. So that's all we're doing, fitting that in here. So notice that, so we get our constant terms. The way that scikit-learn's linear regression returns it back is it has one parameter, which is the intercept term, and then it has the coefficients, which are going to be in order from the x to 1, the x squared, and then higher if we have higher polynomials. So, but this should pretty much match what the NumPy's polynomial is. Right? In fact, I think it's exactly the same. So 0.4929. So yeah, it looks like it's using the exact same optimization probably in both cases. At least down to 6 or 8 decimal places. So, I mean, we could have fit, I mean, not to skip over these, but we could have fit a degree 1 polynomial, Degree 2, we could fit a higher degree of polynomials. So those kind of, when you're doing this sort of trying to fit a nonlinear model by hand, you kind of have to up front decide, okay, what is the degree going to be of the model. So looking at the data, what kind of polynomial you actually need to make a good model. So we could fit a line. Plot that up. So, oh, and also, yeah, you don't have to do this in your fourth assignment, but the same idea works even if I have two features. So, for example, we're just as a real quick example, we're creating X to have 10 samples of two random features here. So, if we displayed what X was before we did the polynomial features fit here. It actually had two columns of these values here between -7 or 7. So the resulting actually ends up with 9 columns because we get all of the combinations as well, right? So if I want to fit a degree 2, or in this case a degree 3 polynomial, I want not only the cubed term of this and the cubed term of this, but I want the a squared times b and the a times b squared, right? So these are all the combinations, as well as the lower squared terms. We want the a squared, the b squared, a cubed, b cubed, but also a b squared, b. So that's, if you work it out for degree 3, there are 9 combinations. We get the original 2 features, so you call this AB or X1, X2, and then this is A times B, X1 times X2, X2 squared, A squared, so X1 squared. So that's all the polynomial. But yeah, if you have more than one feature, you get more terms than just the square, the cube, but also these combinations. And you can see, so this kind of fitting of a nonlinear set of data by hand is not normally done. So if I have 100 features, I have a huge number of combinations here. Right? So you get an explosion of the number of polynomial combinations. Continue this idea. So you have to do something kind of different once you start getting into a realistic, larger number of features to do a nonlinear model. Okay. So, I don't have enough time to cover all this in detail here, but so another part of the assignment is going to get into this concept of learning curves. So we already looked at these a little bit when we did the gradient descent. So what we mean by a learning curve is as we're doing optimization, trying to go towards lower cost. So what we did before is for each iteration, each epoch, we updated our parameters and we tracked how cost was hopefully decreasing as we're getting closer and closer to the global optimum defined by our cost. And that's really what learning curves are, although we do a slightly different for assignment 4 here. Show that. But I think the last thing in the 10 minutes I have is I will mentioned this idea of underfitting and overfitting. We'll maybe come back to this on Thursday. So learning curves we're basically going to be using this in our assignment 4. And in general, in machine learning, learning curves are a useful tool in order to determine whether I've got a model that's doing well, or whether my model is underperforming, so it's underfitting, or my model is overfitting. So as a last thing here, you can always, so we're using the same data that we did before, or similar. So we have a quadratic function. So our true function is this one here. So it's still 1/2 x squared plus 3/4 x plus 3 with some noise. Although I don't remember why. I do remember why we changed the range from -1 to 1. But it really is the same part. So you can imagine fitting a line to this data. So if you're only looking at this, it might not be clear that you need a nonlinear model. So a line might work more quadratic. So the point about overfitting is for machine learning models like this, you can always fit. So in this case, the green is we do a degree 300 polynomial. We can make it even bigger. And as this kind of shows, the more parameters you have, the more wiggle room you give for the function that you're going to optimize. Right? So at the extreme, we're getting close to this. So at the extreme, you have so many parameters, you can find a model that will go through pretty much like every point that you have here. So you can kind of see that with the degree 300 wiggles, so especially at the ends. There's a lot more of that in the middle. But I mean, is that the question is that actually a better model? So we know that the true model was generated with a degree 2, so quadratic, but with a little bit of noise. Right? So if you're doing something like this with a huge number of parameters, you're not really getting a good model. You're getting a model that's modeling the noise in the data. So the point for overfit, the reason why overfit models aren't good models is think of if I have a point here, and I want to make a prediction. So my prediction is going to be, for that point, is going to be like here because of the way this model is working. So we're going to have a huge error. So it will minimize the error for the points you fit with, but when you go to make predictions on points that weren't in the original data you fit with, if you're overfitting, you're going to find that your error is much worse than a simpler model, than a non-overfit model. Because the quadratic or even the linear is going to make much more reasonable predictions because it's mostly modeling, it's not overfitting, so it's not trying to fit the noise in here. It's generalized. So the term that you'll see that our textbook uses is a good model is one that generalizes correctly. So it's fitting to the true function and mostly ignoring the noise that might be. Overfit models don't generalize. And underfit models, so you don't get as good of a feel for this, but if your model is too underpowered, it will also not do well. But that will be because it can't. So if I have a true function is something like this, a linear one, there's no way to get it to be real good in some ranges. It's not powerful. And the linear one in this range probably doesn't do that very much. Okay, I think that's a good place to stop then for today. So, I mean, that's kind of the beginnings. So we'll get into the underfitting and overfitting and how we use these learning curves on Thursday, which is most of the assignment is that. And then next week we'll talk about regularization. So how you fit, how you fight overfitting in models like this. All right. Yep. Yep. Yes. Yeah. Try and at least have something that acts as just a title for the commit, and then there should be like a blank line, and then a sentence or more.